हेलो एवरीवन, वेलकम बैक टू माय चैनल। तो आज के वीडियो में हम देखने वाले हैं एनसीईआरटी क्लास 12 का इकोनॉमिक्स, जिसमें आज हम देखेंगे चैप्टर 3 जो कि है प्रोडक्शन एंड कॉस्ट। तो शुरू करते हैं हमारा आज का चैप्टर। इन द प्रीवियस चैप्टर वी हैव डिस्कस्ड द बिहेवियर ऑफ द कंज्यूमर्स। इन दिस चैप्टर एज वेल एज इन द नेक्स्ट वी शैल एग्जामिन द बिहेवियर ऑफ ए प्रोड्यूसर। Production is the process by which inputs are transformed into output. Production is carried out by a producer or farms. A farm acquires different inputs like labor, machines, land, raw materials, etc. It uses these inputs to produce output. This output can be consumed by consumers or used by other farms for further production. For example, a tailor uses a sewing machine, cloth, thread, and his own labor to produce shirts. A farmer uses his land, labor, a tractor, seed, fertilizer, water, etc. to produce wheat. A car manufacturer uses land for a factory, machinery, labor, and various other inputs, steel, aluminum, rubber, etc. to produce cars. A rickshaw puller uses a rickshaw and his own labor to produce rickshaw rides. A domestic helper uses her labor to produce cleaning services. We make certain simplifying assumptions to start with. Production is instantaneous. In our very simple model of production, no time elapses between the combination of the inputs and the production of the output. We also tend to use the terms production and supply synonymously and often interchangeably. In order to acquire inputs, a farm has to pay for them. This is called the cost of production. Once output has been produced, the farm sells it in the market and earns revenue. The difference between the revenue and the cost is called the farm's profit. We assume that the objective of a farm is to earn the maximum profit that it can. In this chapter, we will discuss the relationship between inputs and output. Then we look at the cost structure of the farm. We do this to be able to identify the output at which farm's profits are maximum. Production function. The production function of a farm is a relationship between inputs used and output produced by the farm. For various quantities of inputs used, it gives the maximum quantity of output that can be produced. Consider the farmer we mentioned above. For simplicity, we assume that the farmer uses only two inputs to produce wheat, land and labor. A production function tells us the maximum amount of wheat he can produce for a given amount of land that he uses and a given number of hours of labor that he performs. Suppose that he uses 2 hours of labor per day and 1 hectare of land to produce a maximum of 2 tons of wheat. Then a function that describes this relation is called a production function. One possible example of the form this could take is Q equals to K into L, where Q is the amount of wheat produced, K is the area of land in hectares, L is the number of hours of work done in a day. Describing a production function in this manner tells us the exact relation between inputs and outputs. If either K or L increase, Q will also increase. For any L and any K, there will be only one Q. Since by definition we are taking the maximum output for any level of inputs, a production function deals only with the efficient use of inputs. Efficiency implies that it is not possible to get any more output from the same level of inputs. A production function is defined for a given technology. It is the technological knowledge that determines the maximum levels of output that can be produced using different combinations of input. If the technology improves, the maximum levels of output obtainable for different input combination increases. We then have a new production function. The inputs that a farm uses in the production process are called factors of production. In order to produce output, a farm may require any number of different inputs. However, for the time being, here we consider a farm that produces output using only two factors of production, labor and capital. Our production function therefore tells us the maximum quantity of output Q that can be produced by using different combination of these two factors of productions, labor and capital. We may write the production function as Q equals to F of Lk, where L is the labor and K is the capital, and Q is the maximum output that can be produced. A numerical example of production function is given in table 3.1. The left column shows the amount of labor and the top row shows the amount of capital. As we move to the right along any row, capital increases and as we move down along any column, labor increases. For different values of the two factors, the table shows the corresponding output levels. For example, with 1 unit of labor and 1 unit of capital, the farm can produce at most 1 unit of output. With 2 units of labor and 2 units of capital, it can produce at most 10 units of output. With 3 units of labor and 2 units of capital, it can produce at most 18 units of output, and so on. In our example, both the inputs are necessary for the production. If any of the inputs becomes 0, there will be no production. With both inputs positive, output will be positive. As we increase the amount of any input, output increases. Isoquant. In chapter 2, we have learned about indifference curves. Here we introduce a similar concept known as isoquant. It is just an alternative way of representing the production function. Consider a production function with two inputs, labor and capital. An isoquant is the set of all possible combinations of the two inputs that yield the same maximum possible level of output. Each isoquant represents a particular level of output and is labeled with that amount of output. Let us return to table 3.1. Notice that the output of 10 units can be produced in three ways: 4L 1K, 2L 2K, 1L 4K. All these combinations of LK lie on the same isoquant, which represents the level of output 10. Can you identify the sets of inputs that will lie on the isoquant Q equals to 50? The diagram here generalizes this concept. We place L on the x-axis and K on the y-axis. We have three isoquants for the three output levels, namely Q equals to Q1, Q equals to Q2 and Q equals to Q3. Two input combinations L1K2 and L2K1 gives us the same level of output Q1. If we fix capital at K1 and increase labor to L3, output increases and we reach a higher isoquant Q equals to Q2. When marginal products are positive with greater amount of one input, the same level of output can be produced only using lesser amount of the other. Therefore, isoquants are negatively sloped. The short run and the long run. Before we begin with any further analysis, it is important to discuss two concepts, the short run and the long run. In the short run, at least one of the factors, labor or capital, cannot be varied and therefore remains fixed. In order to vary the output level, the firm can vary only the other factor. The factor that remains fixed is called the fixed factor, whereas the other factor which the firm can vary is called the variable factor. Consider the example represented through table 3.1. Suppose in the short run, capital remains fixed at 4 units, then the corresponding column shows the different levels of output that the firm may produce using different quantities of labor in the short run. In the long run, all factors of production can be varied. A firm, in order to produce different levels of output in the long run, may vary both the inputs simultaneously. So, in the long run, there is no fixed factor. For any particular production process, long run generally refers to a longer time period than the short run. For different production processes, the long run periods may be different. It is not advisable to define short run and long run in terms of, say, days, months, or years. We define a period as long run or short run simply by looking at whether all the inputs can be varied or not. Total product, average product, and marginal product. Total product. Suppose we vary a single input and keep all other inputs constant, then for different levels of that input, we get different levels of output. This relationship between the variable input and output, keeping all other inputs constant, is often referred to as total product of the variable input. Let us again look at table 3.1. Suppose capital is fixed at 4 units. Now in table 3.1, we look at the columns where capital takes the value 4. As we move along the column, we get the output values for different values of labor. This is the total product of labor scheduled with K2 equals to 4. This is also sometimes called total return or 2 or total physical product of the variable input. This is shown again in the second column of table 3.2. Once we have defined total product, it will be useful to define the concept of average product and marginal product. They are useful in order to describe the contribution of the variable input to the production process. Average product. Average product is defined as the output per unit of variable input. We calculate it as APL equals to TPL by L. The last column of table 3.2 gives us a numerical example of average product of labor with capital fixed at 4 for the production function described in table 3.1. Values in this column are obtained by dividing TP by L. Marginal product. Marginal product of an input is defined as the change in output per unit of change in the input when all other inputs are held constant. When capital is held constant, the marginal product of labor is MP of L equals to change in output by change in input equals to del TPL by del L, where del represents the change of variable. The third column of table 3.2 gives us a numerical example of marginal product of labor with capital fixed at 4 for the production function described in table 3.1. Values in this column are obtained by dividing change in TP by change in L. For example, when L changes from 1 to 2, TP changes from 10 to 24. MPL equals to TP at L units minus TP at L minus 1 unit. Here change in TP equals to 24 minus 10 equals to 10. Change in L equals to 1. Marginal product of the second unit of labor equals to 14 by 1 equals to 14. Since inputs cannot take negative values, marginal product is undefined at 0 level of input employment. For any level of an input, the sum of marginal products of every preceding unit of that input gives the total product. So total product is the sum of marginal products. Average product of an input at any level of employment is the average of all marginal products up to that level. Average and marginal products are often referred to as average and marginal returns, respectively, to the variable input. The law of diminishing marginal product and the law of variable proportions. If we plot the data in table 3.2 on graph paper, placing labor on the x-axis and output on the y-axis, we get the curves shown in the diagram below. Let us examine what is happening to TP. Notice that TP increases as labor input increases, but the rate at which it increases is not constant. An increase in labor from 1 to 2 increases TP by 10 units. An increase in labor from 2 to 3 increases TP by 12. The rate at which TP increases, as explained above, is shown by the MP. Notice that MP first increases up to 3 units of labor and then begins to fall. This tendency of MP to first increase and then fall is called the law of variable proportion or the law of diminishing marginal product. Law of variable proportion says that the marginal product of a factor input initially rises with its employment level, but after reaching a certain level of employment, it starts falling. Why does this happen? In order to understand this, we first define the concept of factor proportions. Factor proportions represent the ratio in which the two inputs are combined to produce output. As we hold one factor fixed and keep increasing the other, the factor proportions change. Initially, as we increase the amount of the variable input, the factor proportions become more and more suitable for the production and marginal product increases. But after a certain level of employment, the production process becomes too crowded with the variable input. Suppose table 3.2 describes the output of a farmer who has 4 hectares of land and can choose how much labor he wants to use. If he uses only one worker, he has too much land for the worker to cultivate alone. As he increases the number of workers, the amount of labor per unit land increases, and these workers add proportionally more and more to the total output. Marginal product increases in this phase. When the fourth worker is hired, the land begins to get crowded. Each worker now has insufficient land to work efficiently, so the output added by each additional worker is now proportionally less. The marginal product begins to fall. We can use this observation to describe the general shapes of the TP, MP, and AP curves as below. Shapes of total product, marginal product, and average product curves. An increase in the amount of one of the inputs keeping all other inputs constant results in an increase in output. Table 3.2 shows how the total product changes as the amount of labor increases. The total product curve in the input-output plane is a positively sloped curve. Figure 3.1 shows the shape of the total product curve for a typical farm. We measure units of labor along the horizontal axis and output along the vertical axis. With L units of labor, the farm can at most produce Q1 units of output. According to the law of variable proportions, the marginal product of an input initially rises and then after a certain level of employment it starts falling. The MP curve therefore looks like an inverse U-shaped curve as in figure 3.2. Let us now see what the AP curve looks like. For the first unit of the variable input, one can easily check that the MP and the AP are same. Now as we increase the amount of input, the MP rises. AP, being the average of marginal products, also rises, but rises less than MP. Then after a point the MP starts falling. However, as long as the value of MP remains higher than the value of the AP continues to rise. Once MP has fallen sufficiently, its value becomes less than the AP and the AP also starts falling. So AP curve is also inverse U-shaped. As long as the AP increases, it must be the case that MP is greater than AP. Otherwise, AP cannot rise. Similarly, when AP falls, MP has to be less than AP. It follows that MP curve curves AP curve from above at its maximum. Figure 3.2 shows the shape of AP and MP curves for a typical farm. The AP of factor 1 is maximum at L. To the left of L, AP is rising and MP is greater than AP. To the right of L, AP is falling and MP is less than AP. Returns to scale. The law of variable proportion arises because factor proportion change as long as one factor is held constant and the other is increased. What if both factors can change? Remember that this can happen only in the long run. One special case in the long run occurs when both factors are increased by the same proportion or factors are scaled up. When a proportional increase in all inputs results in an increase in output by the same proportion, the production function is said to display constant returns to scale, CRS. When a proportional increase in all inputs results in an increase in output by a larger proportion, the production function is said to display increasing returns to scale, IRS. Decreasing returns to scale, DRS, holds when a proportional increase in all inputs results in an increase in output by a smaller proportion. For example, suppose in a production process all inputs get doubled. As a result, if the output gets doubled, the production function exhibits CRS. If the output is less than doubled, then DRS holds, and if it is more than doubled, then IRS holds. Returns to scale. Consider a production function Q equals to f of x1 x2, where the farm produces Q amount of output using x1 amount of factor 1 and x2 amount of factor 2. Now suppose the farm decides to increase the employment level of both the factor t greater than 1 times. Mathematically, we can say that the production function exhibits constant returns to scale if we have f of tx1 tx2 equals to t into f of x1 x2. That means the new output level f of tx1 tx2 is exactly t times the previous output level f of x1 x2. Similarly, the production function exhibits increasing returns to scale if f of tx1 tx2 greater than t into f of x1 x2. It exhibits the decreasing returns to scale if f of tx1 tx2 less than t into f of x1 x2. Cost. In order to produce output, the farm needs to employ inputs. but a given level of output typically can be produced in many ways. There can be more than one input combinations with which a farm can produce a desired level of output. In table 3.1, we can see that 50 units of output can be produced by three different input combinations. L equals to 6, K equals to 3, L equals to 4, K equals to 4, and L equals to 3, K equals to 6. The question is, which input combination will the farm choose? With the input prices given, it will choose that combination of inputs which is least expensive. So, for every level of output, the farm chooses the least cost input combination. Thus, the cost function describes the least cost of producing each level of output given prices of factors of production and technology. Cobb-Douglas production function. Consider a production function Q equals to x1 to the power alpha, x2 to the power beta, where alpha and beta are constants. The farm produces Q amount of output using x1 amount of factor 1 and x2 amount of factor 2. This is called a Cobb-Douglas production function. Suppose with x1 equals to x1 bar and x2 equals to x2 bar, we have Q0 units of outputs. That means Q0 equals to x1 bar to the power alpha, x2 bar to the power beta. If we increase both the inputs t greater than 1 times, we get the new output Q1 equals to tx1 bar to the power alpha, tx2 to the power bar to the power beta equals to t to the power alpha plus beta, k1 bar to the power alpha, k2 bar to the power beta. Where alpha plus beta equals to 1, we have q1 equals to tq0, that is, the output increases t times. So the production function exhibits CRS. Similarly, when alpha plus beta greater than 1, the production function exhibits IRS. When alpha plus beta less than 1, the production function exhibits DRS. Short run cost. We have previously discussed the short run and the long run. In the short run, some of the factors of production cannot be varied and therefore remains fixed. The cost that a farm incurs to employ these fixed inputs is called the total fixed cost, TFC. Whatever amount of output the farm produces, this cost remains fixed for the farm. To produce any required level of output, the farm in the short run can adjust only variable inputs. Accordingly, the cost that a farm incurs to employ these variable inputs is called the total variable cost. Adding the fixed and the variable cost, we get the total cost of a farm. TC equals to TPC plus TFC. In order to increase the production of output, the farm must employ more of the variable inputs. As a result, total variable cost and total cost will increase. Therefore, as output increases, total variable cost and total cost increase. In table 3.3, we have an example of cost functions of a typical farm. The first column shows different levels of output. For all levels of output, the total fixed cost is Rs 20. Total variable cost increases as output increases. With output 0, TVC is 0. For 1 unit of output, TVC is Rs 10. For 2 units of output, TVC is Rs 18, and so on. In the fourth column, we obtain the total cost as the sum of the corresponding values in the second column, TFC, and the third column, TVC. At 0 level of output, TC is just the fixed cost and hence equal to Rs 20. For 1 unit of output, total cost is Rs 30. For 2 units of output, the TC is Rs 38, and so on. The short run average cost incurred by farm is defined as the total cost per unit of output. We calculate it as SAC equals to TC by Q. In table 3.3, we get the SAC column by dividing the values of the fourth column by the corresponding values of the first column. At 0 output, SAC is undefined. For the first unit, SAC is Rs 30. For 2 units of output, SAC is Rs 19, and so on. Similarly, the average variable cost ABC is defined as the total variable cost per unit of output. We calculate it as AVC equals to TBC by Q. Also, average fixed cost AFC is AFC equals to TFC by Q. Clearly, SAC equals to ABC plus AFC. In table 3.3, we get the AFC column by dividing the values of the second column by the corresponding values of the first column. Similarly, we get the ABC column by dividing the values of the third column by the corresponding values of the first column. At zero level of output, both AFC and ABC are undefined. For the first unit of output, AFC is rupees 20 and ABC is rupees 10. Adding them, we get the SEC equal to rupees 30. The short-run marginal cost SMC is defined as the change in total cost per unit of change in output. SMC equals to change in total cost by change in output equals to del C upon del Q, where del represents the change in the value of the variable. The last column in table 3.3 gives a numerical example for the calculation of SMC. Values in this column are obtained by dividing the change in TC by the change in output at each level of output. Thus, at Q equals to 5, change in TC equals to TC at Q equals to 5 minus TC at Q equals to 4 equals to 53 minus 49 equals to 4. Change in Q equals to 1. SMC equals to 4 by 1 equals to 4. Just like the case of marginal product, marginal cost also is undefined at zero level of output. It is important to note here that in the short run, fixed cost cannot be changed. When we change the level of output, whatever change occurs to total cost is entirely due to the change in total variable cost. So in the short run, marginal cost is the increase in TVC due to the increase in production of one extra unit of output. For any level of output, the sum of marginal cost up to that level gives us the total variable cost at that level. One may wish to check this from the example represented through table 3.3. Average variable cost at some level of output is therefore the average of all marginal cost up to that level. In table 3.3, we see that when the output is 0, SMC is undefined. For the first unit of output, SMC is rupees 10. For the second unit, SMC is rupees 8 and so on. Shapes of the short-run cost curves. Now let us see what these short-run cost curves look like. You could plot the data from table 3.3 by placing output on the x-axis and cost on the y-axis. Previously, we have discussed that in order to increase the production of output, the farm needs to employ more of the variable inputs. This results in an increase in total variable cost and hence an increase in total cost. Therefore, as output increases, total variable cost and total cost increase. Total fixed cost, however, is independent of the amount of output produced and remains constant for all levels of production. Figure 3.3 illustrates the shapes of total fixed cost, total variable cost, and total cost curves for a typical farm. We place output on the x-axis and cost on the y-axis. TFC is a constant which takes the value C1 and does not change with the change in output. It is therefore a horizontal straight line cutting the cost axis at the point C1. At Q1, TVC is C2 and TC is C3. AFC is the ratio of TFC to Q. TFC is a constant, therefore as Q increases, AFC decreases. When output is very close to 0, AFC is arbitrarily large, and as output moves towards infinity, AFC moves towards 0. AFC curve is in fact a rectangular hyperbola. If we multiply any value Q of output with its corresponding AFC, we always get a constant, namely TFC. Figure 3.4 shows the shape of average fixed cost curve for a typical farm. We measure output along the horizontal axis and AFC along the vertical axis. At Q1 level of output, we get the corresponding average fixed cost at F. The TFC can be calculated as TFC equals to AFC into quantity equals to OF into OQ1 equals to the area of the rectangle OFC Q1. We can also calculate AFC from TFC curve. In figure 3.5, the horizontal straight line cutting the vertical axis at F is the TFC curve. At Q0 level of output, total fixed cost is equals to OF. At Q0, the corresponding point on the TFC curve is A. Let the angle AOQ0 Q naught be theta. The AFC at Q naught is AFC equals to TFC by quantity equals to AQ naught by OQ naught equals to tan theta. Let us now look at the SMC curve. Marginal cost is the additional cost that a firm incurs to produce one extra unit of output. According to the law of variable proportion, initially the marginal product of a factor increases as employment increases, and then after a certain point it decreases. This means initially to produce every extra unit of output, the requirement of the factor becomes less and less, and then after a certain point it becomes greater and greater. As a result, with the factor price given, initially the SMC falls and then after a certain point it rises. As SMC curve is therefore U-shaped. At zero level of output, SMC is undefined. The TBC at a particular level of output is given by the area under the SMC curve up to that level. Now, what does the ABC curve look like? For the first unit of output, it is easy to check that SMC and ABC are the same. So, both SMC and ABC curves start from the same point. Then, as output increases, SMC falls. ABC, being the average of marginal cost, also falls, but falls less than SMC. Then after a point, SMC starts rising. ABC, however, continues to fall as long as the value of SMC remains less than the prevailing value of ABC. Once the SMC has risen sufficiently, its value becomes greater than the value of ABC. The ABC then starts rising. The ABC curve is therefore U-shaped. As long as ABC is falling, SMC must be less than the ABC. As ABC rises, SMC must be greater than the ABC. So the SMC curve cuts the ABC curve from below at the minimum point of ABC. In figure 3.7, we measure output along the horizontal axis and TBC along the vertical axis. At Q0 level of output, OV is the total variable cost. Let the angle EOQ0 be equal to theta. Then at Q0, the ABC can be calculated as ABC equals to TBC by output equals to EQ0 by OQ0 equals to tan theta. In figure 3.6, we measure output along the horizontal axis and ABC along the vertical axis. At Q0 level of output, ABC is equal to OV. The total variable cost at Q0 is TBC equals to ABC into quantity equals to OV into OQ0 equals to the area of the rectangle OVBQ0. Let us now look at SAC. SAC is the sum of ABC and AFC. Initially, both ABC and AFC decrease as output increases. Therefore, SAC initially falls. After a certain level of output production, ABC starts rising, but AFC continues to fall. Initially, the fall in AFC is greater than the rise in ABC, and SAC is still falling. But after a certain level of production, rise in ABC becomes larger than the fall in AFC. From this point onwards, SAC is rising. SAC curve is therefore U-shaped. It lies above the ABC curve with the vertical difference being equal to the value of AFC. The minimum point of SAC curve lies to the right of the minimum point of ABC curve. Similar to the case of ABC and SMC, as long as SAC is falling, SMC is less than the SAC. When SAC is rising, SMC is greater than the SAC. SMC curve cuts the SAC curve from below at the minimum point of SAC. From figure 3.8, the shapes of short-run marginal cost, average variable cost, and short-run average cost curves for a typical firm. ABC reaches its minimum at Q1 units of output. To the left of Q1, ABC is falling and SMC is less than ABC. To the right of Q1, ABC is rising and SMC is greater than ABC. SMC curve cuts the ABC curve at P, which is the minimum point of ABC curve. The minimum point of SAC curve is S, which corresponds to the output Q2. It is intersection point between SMC and SAC curves. To the left of Q2, SAC is falling and SMC is less than SAC. To the right of Q2, SEC is rising and SMC is greater than SEC. Long run cost. In the long run, all inputs are variable. There are no fixed costs. The total cost and the total variable cost therefore coincide in the long run. Long run average cost LRAC is defined as cost per unit of output. That means LRAC equals to TC by Q. Long run marginal cost LRMC is the change in the total cost per unit of change in output. When output changes in discrete units, then if we increase production from Q1 minus to Q1 units of output, the marginal cost of production Q1th unit will be measured as LRMC equals to TC at Q1 units minus TC at Q1 minus 1 units. Just like the short run, in the long run, the sum of all marginal costs up to some output level gives us the total cost at that level. Shapes of the long run cost curves. We have previously discussed the returns to scales. Now let us see their implications for the shape of LRAC. IRS implies that if we increase all the inputs by a certain proportion, output increases by more than that proportion. In other words, to increase output by a certain proportion, inputs need to be increased by less than that proportion. With the input prices given, cost also increases by a lesser proportion. For example, suppose we want to double the output. To do that, input needs to be increased, but less than double. The cost that the farm incurs to hire those inputs, therefore, also need to be increased, but by less than double. What is happening to average cost here? It must be the case that as long as IRS operates, average cost falls as the farm increases output. DRS implies that if we want to increase the output by a certain proportion, inputs need to be increased by more than that proportion. As a result, cost also increases by more than that proportion. So, as long as DRS operates, the average cost must be rising as the farm increases output. CRS implies a proportional increase in inputs resulting in a proportional increase in output. So, the average cost remains constant as long as CRS operates. It is argued that in a typical farm, IRS is observed at the initial level of production. This is then followed by the CRS and then by the DRS. Accordingly, the LRAC curve is a U-shaped curve. Its downward sloping part corresponds to IRS and upward rising part corresponds to DRS. At the minimum point of the LRAC curve, CRS is observed. Let us check how the LRMC curve looks like. For the first unit of output, both LRMC and LRAC are the same. Then as output increases, LRAC initially falls and then after a certain point it rises. As long as average cost is falling, marginal cost must be less than the average cost. When the average cost is rising, marginal cost must be greater than the average cost. LRMC curve is therefore a U-shaped curve. It curves the LRAC curve from below at the minimum point of the LRAC. Figure 3.9 shows the shapes of the long-run marginal cost and the long-run average cost curves for a typical farm. LRAC reaches its minimum at Q1. To the left of Q1, LRAC is falling and LRMC is less than the LRAC curve. To the right of Q1, LRAC is rising and LRMC is higher than LRAC. तो ये है इस चैप्टर का समरी और ये है इस चैप्टर के एक्सरसाइजेस और इसी के साथ हमारा चैप्टर नंबर 3 कंप्लीट हो गया है। तो अगर आप चैनल पे नए हैं तो चैनल को सब्सक्राइब कर दीजिए और नोटिफिकेशन आइकन पर क्लिक कर दीजिए ताकि आपको सारे वीडियोस के अपडेट्स मिल सकें। और अगर आपको वीडियो अच्छा लगे तो लाइक कर दीजिए और अपने दोस्तों के साथ शेयर कीजिए ताकि उन्हें भी हेल्प हो सके। तो आज के वीडियो में हमने चैप्टर 3 कंप्लीट कर दिया है। तो हमारा ये वीडियो यहीं तक था। थैंक यू, थैंक्स फॉर वॉचिंग।